Welcome to Summarize Science. Our home galaxy, the Milky Way, holds a secret history written in the stars themselves. A team of researchers recently conducted a massive study to map out a specific group of ancient stars known as the High Alpha disk. They focused on subgiant stars, which are perfect for this kind of research because their ages can be determined very accurately. By combining data from the Lemmost and Gaia space surveys, they analyzed about 45,000 of these stellar veterans. The researchers wanted to look past just the current position of these stars. Instead, they focused on orbital cartography, which maps out the entire path a star takes around the center of the galaxy. This approach is like looking at a person's lifelong habits rather than just where they are standing right now. They found that the oldest stars have much more dramatic, vertical orbits compared to the younger stars in this group. These maps show clear gradients, meaning the chemical makeup of stars changes predictably based on how they move. For example, stars that are metal-poor tend to have much more chaotic, looping orbits. In contrast, stars with more iron and fewer alpha elements follow more circular and orderly paths. This discovery is significant because it suggests the Milky Way was not just a random mess in its early days. The team found evidence for what they call inside-out and upside-down growth. This means the galaxy started forming in the center and gradually grew outward, while also flattening over time. One of the most shocking findings involves the history of galactic collisions. Scientists used to think major mergers, like the one with the Gaia-Enceladus galaxy, would have scrambled the history of the stars. However, this study shows that the ancient structure of the High Alpha disk survived these massive impacts. This implies that the Milky Way is remarkably good at preserving its fossil record of early assembly. To recap, the researchers used precise ages and chemical tags to show that our galaxy has a highly organized structure dating back billions of years. They proved that even ancient stellar maps can survive massive space collisions. In the future, this method will help us understand the early lives of other galaxies across the universe. Knowing how our own home formed gives us the ultimate context for our place in the cosmos. By looking at the dispersion of these chemicals, they confirmed their findings weren't just a fluke in the data. Even the younger parts of the disk show similar patterns, suggesting a continuous story of growth. This research is a giant leap forward in our quest to map the biography of the Milky Way.